Today we're going to take a look at lesson 2.2, proving that lines are parallel. We'll go ahead and start up here in this critique and explain section. So 1 analyzes the diagram to see if line L is parallel to line M. So what's happening here is they're not outright telling 1 that these two lines are parallel. Sure, they look parallel, but they need to specifically either state that they're parallel or they have to have those little tick marks on them showing that they're parallel. You can't just assume based off of a visual inspection that they're parallel. The information has to be there. His teacher asks if there's enough information to say whether the lines are parallel. So what you're seeing here is they're not telling you that the lines are parallel, but look at the other information they're giving you. They're saying that angle 1 is congruent to angle 4. I know that because there's only one tick mark for both of those angles. And then angle 2 is congruent to angle 3. I know that because there's 2 tick marks for both of those angles. So based off of that information, I think we can say that those two lines are parallel. Let's keep reading. So their answer is, the question was, his teacher asked if there's enough information to say whether the lines are parallel. Yes. If a transversal, so again, that's this line that cuts those two lines at any angle. I mean, it could be super shallow like this. It could be really steep, almost straight up and down. It doesn't matter what the angle is. It just has to cross both of those lines. If a transversal intersects two parallel lines, then alternate interior angles, so they're referring to angle 2 and angle 3, are congruent and corresponding angles are congruent. So angle 1 and angle 4 are corresponding angles. It doesn't necessarily have to have both of those relationships. It just has to have one, but in this case, they have both. So it says, I have both angle relationships here, so the lines are parallel. Example 1. This is a tricky example, and I'm going to do my best to explain it. This example is more of a proof, proving that something can or can't happen. It's going to be pretty intense, so make sure you're following along with me. Suppose two lines are not parallel. So they're telling you right off the bat that these two lines are not parallel. Can corresponding angles still be congruent? Can they still be equal? So let's keep looking. We're going to read through each of these pieces, and as I read through them, I'll point out where they're talking about. So they want you to draw two parallel lines, T and M, and a transversal S. So here's line T, there's line M, and there's our transversal S. Okay? You could see that T and M are not parallel. They're actually crossing right on the page, and they're telling you they're not parallel in the beginning, so you know that they're not. All right. Draw line L that's parallel to M. So here's line L, that's that dotted line. It's parallel to M. I know that, well, because they're telling me that there, but also see these little red arrows? That's showing that those two lines are parallel to each other. Draw line L parallel to M that passes through the intersection of S and T. So again, S is that transversal. T is that other non-parallel line to M. So line L will cross at that intersection. All right, let's read their little clouds of information here. Lines T and M are not parallel. We already established that. M is just a line. T is not parallel to M. The transversal S intersects line T and line M. So here's our transversal. It intersects both line T, the other non-parallel line, and line M, which is the pair of the parallel lines, right? It's paired with L. So line S, let me read this again. Transversal S, so there we go, intersects lines T and M. So there's T, there's M. The 120-degree angle corresponds with the angle formed by combining 1 and 2. So if I add these two, let me go ahead and erase this. If I added these two angles here, angle 1 and angle 2, they're going to equal 120 degrees. Okay. So here's their justification. Here's their proof of what they're saying is or isn't true. We'll see at the end. Since L is parallel to M, right? We drew line L specifically to be parallel to line M. The measure of angle 1 is equal to 120. So here's kind of a difficult part of this. So the measure of angle 1 is equal to 120. I think the difficult part of this that students get tripped up on, or even I get tripped up on too, it's hard for me to visually imagine this, right? Is you've got all these different lines on this page, right? Well, right now, you are completely ignoring line T. You should, or hopefully you can, like, erase it in your vision. So you're only focused on the two parallel lines and the transversal S. Okay? This line T, try to ignore it. Try to just, blank it out of your picture here. Try to just visually see M and L and then transversal S. And then you should be able to see that 120 corresponds with angle 1, so they're equal to each other. By the alternate interior angles theorem, the measure of angle 2 equals x. So no, we're not looking at the transversal S anymore. We're looking at the transversal T. So I'm going to erase my pencil marks on here. Now, again, still look at lines L and M, but we're looking at this transversal now. So ignore S, try to erase it. This is our transversal. So they're saying that angle 2 is equal to x. So their final statement, since the measure of angle 1 plus the measure of angle 2, so they're saying since this plus this is the same thing, it's equal to 120, because remember we said angle 1 was equal to 120, and we said that angle 2 was equal to x. So since the measure of angle 1 plus the measure of angle 2 equals 120 plus x, what this is saying is that the measure of angle 1 plus the measure of angle 2 has to be greater than 120. Let me explain that. So we said at the beginning that these two angles together add up to 120 degrees, right? They say it right here in the instructions part of it. Well, what we just proved is that if angle 1 equals 120 and angle 2 equals x, these two angles together added have to be the same thing as these two angles together, 120 and x. Well, at the beginning, we said 1 plus 2, measure of angle 1 plus measure of angle 2 was 120. If I add x to it, regardless if x is 1 or 30 or 25 or whatever, I can't add anything to it because then it contradicts what I was told back in my instructions, that the measure of angle 1 plus the measure of angle 2 equals 120, right? So it's a little bit confusing. It's a lot of steps, a lot of different places you're looking for information, but that is impossible. You can't state that the measure of angle 1 plus the measure of angle 2 equals 120 and then prove that the measure of angle 1 plus the measure of angle 2 equals 120 plus something more. Those two statements contradict each other. So they proved if two lines are not parallel, then corresponding angles are not congruent. They're not equal to each other. All right. Top of page 79, a couple more theorems. Don't forget, theorems is just a fancy word for rules. These are talking about converses of certain theorems. So the converse is pretty much the opposite of the theorem that we already got introduced to. So if you remember, we were introduced to the corresponding angles theorem, that if you have two parallel lines, if lines L and M are parallel, then these two angles, angle 1 and angle 2, must be congruent. They must be equal. So the converse is kind of flipping that, right? It's starting with, if you have two congruent angles 1 and angle 2, then your two lines must be parallel. So it's an if-then statement. What we were talked about before, like I said, was if we have two parallel lines, then angles 1 and angle 2 are congruent. Now we're saying the converse. if angles 1 and 2 are congruent, then we have two parallel lines. Same thing with theorem 2.5, the converse of the alternate interior angle theorem. What we were told in the past is if L and M are parallel, then angles 1 and 2 are congruent. And now we're talking about the converse. If angles 1 and 2 are congruent, then L and M are parallel. For example 2, we are not going to look at this because some of this information, like I explained last week, we didn't get a chance to see. In those proof sections of lesson 1.4 through 1.7 or whatever they were, we skipped those. So we are not going to look at any of these proof examples just because, it's not really a stretch. You could do this, but we missed information in the past, and I don't want to kind of add on what we're learning this week plus all that old information. So you will not be asked to do any type of proof problems like this, like a flow proof. Top of page 80, a couple more theorems. So the converse of the same side interior angles postulate. So again, what we were told before was if L and M are parallel, then angle 1 plus angle 2 has to be equal to 180. Now we're being told if angles 1 and angle 2 add up to 180 degrees, then L and M are parallel. So it's just the opposite of what you were told before. Same thing with theorem 2.7. We were told before if L and M are parallel, then these alternate exterior angles, right? They're on alternating side of the transversal and they're on the outside of the parallel lines. These alternating exterior angles must be congruent. Now they're telling you if angles 1 and 2 are congruent, then lines L and M are parallel. So just the opposite. Example 3. And I think I have a thing written out for this so I can actually draw a picture. All right. Determine whether lines are parallel. So the edges of a new sidewalk must be parallel. So what they're talking about is this left edge of the gray sidewalk and the right edge of the gray sidewalk. Those have to be parallel in order to meet accessibility requirements. Concrete is poured between straight strings. How does an inspector know that the edges of the sidewalk are parallel? Okay. The inspector can first measure the angles of the corners on the sidewalk. So if you take a look, it looks like they're saying that this angle between this road right here and the sidewalk, that angle is 53 degrees. Okay. They're also saying that this angle is 53 degrees. So if you can imagine it, if you have alternate exterior angles, right? Alternate exterior angles, then those lines are parallel. Let me go ahead and show you on my little sketch here. Here's that same sketch, right? Take a look. There's that gray sidewalk. There's the street that runs across the middle. There's 53 degrees. There's 53 degrees. So it should match up with my graph right here, unless I screwed it up. Here are those parallel lines, right? That's that sidewalk that's parallel. Here are, oh, I'm sorry. We're trying to show that this sidewalk is parallel. So that's not given. So please ignore that. That's not given. That's what we're trying to show. They're giving you that this angle here and this angle here are congruent. Here's my parallel, or here's my lines, right? Here's my hopefully parallel lines. There's my transversal. So because of the exterior, the converse of the exterior alternate angles theorem, right? These are on the outside of the parallel lines. They're on alternate sides of that transversal. Because of that, the converse would state that yes, these two lines are parallel, right? Again, here's the sidewalk, the possible parallel lines. There's the transversal. Those are on the alternate exterior angles of that transversal. So because those alternate exterior angles are congruent, then these lines must be parallel. So let's see if that's it. Since the two 53-degree angles are congruent, he can apply the converse of the alternate exterior angles theorem, and the edges of the sidewalks must be parallel. A couple more theorems. So this is saying if two lines are parallel to the same line, then they are parallel to each other. So let me walk you through what they're saying here. You can kind of figure out which lines are parallel to each other. Look at these arrows. So that's like a red or an orange arrow. So that this is indicating that line A and line C are parallel. Here's the double, blue arrow, right? So this is indicating line B and line C are parallel. So what this theorem is stating is if A is parallel to C and B is parallel to C, right? A is parallel to C, B is parallel to C. Well, then what you can conclude, since both of these lines are both parallel to C, you can conclude that A is parallel to B. So since A is parallel to C and B is parallel to C, that shows that A is parallel to B. The second one, if two lines in the same plane are perpendicular to the same line, then they are parallel to each other. So what they're stating is you don't know if A and B are parallel yet, but what they're saying is if I have a transversal C, and this transversal meets both of these lines at a 90-degree angle, right? So you have just two random lines, A and B. You don't know if they're parallel or not. But if this transversal meets both of those lines at a right angle, then it proves that those two lines are parallel to each other. And it really proves it because of the corresponding angle theorem, right? Corresponding angles, if they're congruent, then those two angles are parallel, or those two lines are parallel. All right, example 4. When building a gate, how does Bailey know that the vertical boards, so the up and down boards like this, vertical boards, V and W, are parallel? Well, I think it's going to use that theorem that we just talked about right before, Theorem 2.9. So you could see in this picture that this is board V. It goes straight up like that. This is board W, goes straight up. What they're indicating is that both of those boards join board A. Board A is that basically your transversal, right? Board A, they both join them at a 90-degree angle. Okay. So since both of those boards join board A, they both join the transversal at a 90-degree angle, then they must be parallel. And that, I think, is what they're trying to get here. Use Theorem 2.9, which is the one right above, that same idea, that if those two lines, V and W, right, they're joined by a transversal, in this case, the transversal is board A, as long as those angles are congruent, 90-degree angles, that proves that V and W are parallel. Part B, what should measure of angle 1 measure to ensure board B is parallel to board A? So what should angle 1, which looks like it's right here, this is angle 1, what should that board measure in order to be parallel to board A? So if you want these two boards, board A and board B, to be parallel, then you have to prove that one of those things that we've talked about so far are true. You have to prove alternate interior angles. You have to prove corresponding angles, things like that. Well, one thing we talked about was this supplementary angle. Again, you're only looking at board A, board B, and this is technically your transversal. So board A, board B, and your transversal. What they're saying, if this angle is 35 degrees, and you want to show that these two boards are parallel, well, then these two angles must add up to 180 degrees. So angle 1, what's 180 minus 35? 145? So angle 1 must be 145 degrees. Because we've talked about alternate interior angles, alternate exterior angles, things like that prove that they're congruent. Well, this is another one, supplementary angles, right? So if they add up to 180 degrees, then those two boards are parallel. This is saying apply the converse of the same side interior angles postulate. So I think that is at the top of page 80, theorem 2.6. And it's basically doing the same thing we just said, that those two angles have to add up to 180 degrees if those two boards are parallel. So in order to make them parallel, the measure of angle 1 must be 145. All right, the top of page 82. Concept summary. So it's just kind of applying all those different things. If corresponding angles are congruent, then L is parallel to M. If alternate interior angles are congruent, then L is parallel. If alternate exterior angles are congruent, then L is parallel. If same side interior angles are supplementary, that means they add up to 180 degrees, then they're parallel. If these four things happen, then you're proving that these two lines are parallel to each other. All right. So because we're skipping the proof, the flow proof theorems, we're not going to have a ton of problems to do this week. So let's go ahead and kick this off with problem number 12. Get myself situated here a little bit better. Okay, number 12. For exercises 12 through 15, use the given information. Which lines in the figure can you conclude are parallel? State the theorem that justifies each answer. All right, we're back. Sorry, I had somebody at my door and dog was barking and craziness. Okay, so number 12. Let me go back and read this. For exercises 12 through 15, use the given information. Which lines in the figure can you conclude are parallel? State the theorem that justifies each answer. So you're looking at angles 2 and angle 3. So angle 2 and angle 3. Which lines, based off of that information, that those two things are congruent. So we're looking at 2 and 3. If you know that those two things are congruent, which lines can you conclude are parallel? So that to me looks like if I state that lines P is parallel to line Q. I can state that. So here's my two parallel lines, line P and line Q. I can state that because these are corresponding angles. So 2 and 3 are corresponding angles. So because of the converse of corresponding angles. Remember what they're talking about here when I say converse of corresponding angles. Well, before, you could say because those two lines are parallel, then corresponding angles are congruent. Now they're telling you because these two angles, 2 and 3, are congruent, you've proved that P and Q are that P and Q are parallel. All right, so let's take a look at number 13. Angle 6 and angle 7. So that's these two right here, angle 6 and angle 7. I think we're looking at, again, lines P and Q. So if these two are your possible parallel lines, and this is your transversal, angle 6 and angle 7, if those are congruent, I can state that P is parallel to Q because the converse of alternate interior angles. Theorem, right? I mean, they're all theorems. So again, if you could visually try to imagine this, Q and P are just two lines. S is my transversal. If they're saying that 6 and 7 are congruent, well, that's telling me that Q and P are parallel. Angle 1 and angle 4. So there's angle 1, there's angle 4. So I think they switched over to the other set of parallel lines, or the other set of possible parallel lines, I should say. So what we're talking about now are R and S. Those are the possible parallel lines. And then line Q is our transversal. So try to ignore everything else. Look at S and R as the possible parallel lines, and Q is the transversal. So they're saying that angle 1 is congruent to angle 4. What that tells me is if angle 1 is congruent to angle 4, that R must be parallel to S. I don't know why I drew 2 tick marks above that. It should just be 1. So line R is parallel to line S because of the converse of, again, if these are my 2 parallel lines, this is my transversal. These are alternate exterior angles. Angle 1 and 4 are alternate exterior angles. Alternate exterior angles. Angles. Excuse my crappy penmanship. All right. And then number 15. The measure of angle 5 plus the measure of angle 8 equals 180. So they're saying that this angle right here plus this angle right here adds up to 180 degrees. So what that tells me is we're looking at lines R and S, and then P is my transversal. So try to ignore Q. So if I add angles 5 and 8, and if they add up to 180, then that proves that R and S are parallel. So line R is parallel to line S because of the converse of, these are supplementary angles, so they'll add up to 180 degrees. The book is also calling them same side interior angles. So they're on the same side of the transversal, and they're both on the inside of the parallel lines. So I'm going to state what the book said because of the converse of the same side interior angles. All right. 16 we're skipping because this is talking about the flow proof. 17 and 18 we're skipping because this is again talking about the flow proof. Or, you know, like I said, we skipped out a lesson out of chapter 1. We skipped the proof lessons. So you may have to use information to answer those that we skipped. So I don't even want to introduce it. I don't even want to talk about it. 19. For what value of x is f parallel to g? So for 19. For what value of x is f parallel to g? Which theorem justifies your answer? Well, if you're looking at f and g, those are the possible parallel lines. And then this line right here, they don't have named as your transversal. I think what we have here are alternating exterior angles, right? They're on alternating sides of that transversal, and they're on the exterior part of your parallel lines. Okay, so alternating exterior. If I go back and look, which one was it? Alternating exteriors. That's theorem 2.7 from page 80. The converse of alternating exteriors theorem. So with number 19, they're asking what value of x does x have to be to force those lines to be parallel, to make them parallel. So if I know in order for these 2 lines to be parallel, that those 2 angles have to be congruent, that's exactly what I'm going to do. I'm going to set 10x plus 5 equal to 12x minus 9. So 10x plus 5 equals 12x minus 9. So what I'm doing here is just using algebra, and I'm just going to find the value of x to make them equal to each other. So I'll rewrite this without the parentheses just so we have less junk on our page. I'm going to go ahead and move the x's to the left because when I subtract 10x, it'll just keep that positive on the right-hand side. Since I move my x's to the right-hand side, I'll go ahead and move that constant to the left. So I have 14 equals 2x. My last step, divide by that coefficient, and I have x equals 7. So for number 19, it's actually wondering what value of x will make those lines parallel. So what we found is that when x equals 7, lines F and G will be parallel. And then which theorem justifies your answer? I think we said 2.7. Yep, 2.7 on page 80. So you'd write that again. Theorem 2.7. All right. So with this section, make sure you understand those 4 theorems that they emphasized. Basically this part right, if I can zoom in, right there. Make sure you understand what each one of those things are saying and what each one of those things are doing. Okay. Like we said, just a recap of everything. We've talked about all of these theorems before, but this lesson is focused on the converse of all of these theorems. So basically, before we said, hey, if these 2 lines are parallel, then all these things are true, right? This lesson is saying, if all these things are true, then we know that these 2 lines are parallel. That's what the converse means.